Hello, everybody. I would like to go through the questions as 174, 175, and 177 in calculus section for the work week 9 for the course Maths 1151 at University of New South Wales. In these questions, we are dealing with the improper integrals. Definition of improper integral. We looked at the view this type of integral, one of the boundaries is infinite. When we say the infinite part is just like R, and we think that that is limit R goes to the infinity. So looking at this integral by the perspective of the limit. That's what it is. Convergency. We can talk about the convergency like sums in the discrete sense, and the integrals are in the continuous sense. So when we take the, I think that's what we've done last week. We looked at the Riemann integral. We divided it into intervals and sum it up. And when the intervals get smaller and smaller, infinitely many smaller, then we get a concept of the integral. So that's what an integral means. Now, since we are concerned about the convergency of a sum, also we concern about the convergency of an integral if one of the boundaries are infinite. Definition here, when if there exists an L of the real number such that this limit goes to the L as R goes to the infinity. If such an limit exists, then we say that the integral is convergence to L, it is convergent, or F is integrable. Otherwise, we call it divergent, or not integrable, or diverges. And the compression test help us without calculating each of the convergency of the integrals. We can compare integrals in some way. We can say if one converges, what happens to the other. Very important and most used compression test is given with this idea. Now, this idea, you have the f, and g function is larger than the f function. If g function contracts, if g function contracts, f has to contract. I'm using an analogy here. That analogy is that consider two spheres, two ball of the spheres. One, you have an inside small sphere, a ball, and you have a bigger ball. Now, if your bigger ball contracts, which means converge, then the inside ball has to converge as well, because outside ball is getting smaller and smaller and smaller and getting to the 1 point situation, 1 point state. That is the contraction means. If bigger ball contracts, the inside ball, the smaller ball, has to contract. There's no other option. Okay, this means that the first line, if the inside function, the inside ball explodes as a fusion, it diverges, opens up and explodes, blow up, then it diverges because inside diverge, then outside diverge. But this test gives only the 50% results for you. What I mean by that, if outside ball blow out, you can say nothing about the inside ball. If inside ball contracts to a point, you have nothing to say for the outside ball. So the situation is like a 50% success for this compression rates. This is why you need to be very careful with this when you're comparing your functions. Which side you're taking, which side is convergent, what information you can get. If inside converge, you have nothing to say for the outside one. If outside converge, then you can say inside has to converge too. Because if outsides contract, inside wall has to contract. Or if inside ball explodes, then outside has exploded. But if outside explodes, you can have no information for the inside ball. So please bear this in mind when you are applying the compression test. Limit form is another quick way as a test, is a tool, a big great tool for compression test. You have f and g functions, non-negative and bounded. You're just looking at the limit fx over jx, and if you find a limit which is between 0 and infinite, not infinite itself, it's a finite limit, basically, positive finite limit, then you can say, but if f or g converge, both converge or both diverge. This is in either or situation. If either this happens or this happens, either they're both converge together or both diverge together. So that's the test all about. P integral, there's a theorem which has been proven in your lecture notes. If this P integral converge if P is bigger than 1 and diverge if P is smaller than 1. These are the summary before we start. We are going to use this knowledge when we are solving this problem, going through the solutions of this problem. Okay, if we would like to evaluate the improper integral and show that they diverge, or show that they diverge. Okay, this is a simple, straightforward example. If we take the, so by the definition, we'll view this improper integral as a limit from r goes to the infinity from 0 to r. We know how to integrate this, which is minus 1 over 5 e to the minus 5. The boundaries is 0 r. We place the r minus the e to the 0 case. And when r goes to the infinity, so this will be 0 because e to the minus infinity is 0. E to the, and that is 1 because e to the 0 is 1. We have minus 1, but this is 0 and this is minus 1, so the result will be 1 over 5. Straightforward. For the second one, we have this time minus infinity. So we will take the limit r goes to the minus infinity, 1 over r, from r to 1 integrate. This is a simple function to integrate. That will be minus 1 over that 1 over this constant and exponential E001x. So x will be from r to 1. When we put 1 minus 2r, we obtain this limit. So that exists with this definition, minus 1 divided over 001 will be just the 1 over 100. So there's a negative here. That's a negative. Negative 100 appears here. Then you have when x is equal to 1, when x is equal to r goes to the minus infinity, then this will be plus infinity. E to the infinite is just infinite and swallows everything out, and that will be infinite. That means that this integral is divergent integral. And part C. Now we have this integral. This integral is, we know that it is related. I mean, in our mind, we know, you can look at the table. You will be given by these formulas in the exam time. You don't need to memorize it, but this is a tangent inverse. So we would like to make this one like a similar to this. So taking the 4 out, that's a constant. We have x over 2. We can make the x is over 2 is u. Change this, substitute this new variable. When we take the derivative, that will be du dx over 2. That is 2 du dx. Substitute in, since this is an improper integral, that will convert into the limit. R goes to the infinity when we put R here. So this constant is out when we are turning the u's, and when x is equal to 0, u is equal to 0. When x is equal to r, u is equal to r over 2. This is why the boundaries change. Dx will be 2 du, 1 over 1 plus u squared. So this part will be tangent inverse, and the constant 2 over 4 will be 1 over 2. And if we put the boundaries in, we have r over 2. When r goes to the infinity, this will be tangent inverse infinite, which is the value of pi over 2, tangent inverse 0, which is the value of 0. Then we have pi over 4, because you have a 2 here, pi over 2 times 1 over 2, pi over 4. So that's the result for this integral, this improper integral. Let's have a look at the situation for from minus infinity to plus infinity, how we can solve those ones. We view this improper integral as r goes to the infinity from minus r to the r. Now we need to integrate this quantity. And changing the variable, when let's say x to the 4 is equal to u, and if we derivate it, we have 4x cubed dx du. So x cubed dx will be just du. So when we substitute in, we will have a 1 over 4 e to the minus u du. And when we turn back, 1 over, I'm just doing it without boundaries. I'm just doing it in a corner. So subcalculating this integral without boundaries first. So I have minus 1 over 4 e to the minus 4, e to the x to the 4. So this is the solution for the integral. Now I'm putting the boundaries. Since I turn back to the x, I can use exactly the same boundary. I don't need to turn it back and forward. I put the r's back in, and then one r goes to the infinity. So both of them is, minus infinite, minus infinite. So e to the minus infinite is just 1. E to the minus infinite is 1. 1 minus 1 is 0. So this is 0. If it is 0, it zero, stretches to 0. Okay, this is the E part of this question. So in order to be able to view of this improper integral, this is the limit r. And x minus 1 is here. We want to make it change the variable. X minus 1 is equal to du. So integral itself, let's handle it in a corner. That's du over u to the 3 over 2, u minus 3 over 2. Then the integral of, as we know, this is 1 over minus this constant plus 1. So that's constant plus 1. And that constant plus 1 is just a minus 2 over root 2, right? This is this function. Just to put the back again, u is equal to x minus 1. So I don't need to change the variables at all. If I calculated this one in a corner, put it back to the information. I have minus 2 because of that, and I have that minus 2 to the root 2. If you put r minus x is equal to 2, this is just 1, 1, that's, I'm taking the minus 2 out. That's, if we put the 2 here, 2 minus 1 is 1, root 1 is 1, so it is just 1, that's 1. This is 1 over root minus 1. When r goes to the infinity, this quantity goes to the 0. We only have 2. So the convergence and the calculation gives us the 2. And the part F is the limit. R goes to the infinity. This is the exponential function e, exponential the value e to the infinity. So if we have the dx over x here, and we have ln x, if we say ln x is equal to u, then when we derivate, then we will have du. So that will be just the du over du. That's ln u. That's ln of the ln x is the result for this integration. Straightforward. Take the limit r goes to the infinity. So substitute r first. So we have ln r minus ln e. So ln e is 1, ln 1 is 0. So this is 0. R is equal to infinity. Ln r is infinite. Ln infinite is infinite. So this is infinite. So that's infinite. It means that the integral itself diverges. Okay, now question 175 deals with the comparison test. Comparison test determine whether or not the improper integral converges. Okay, now this is a polynomial. When we have a polynomial, what we need to remind ourselves, recall the p integral. P integral is this integral converge if p is greater than 1, is diverge if p is smaller than 1. And also we can use the limit test, or we can use the convergency test. Let's see whatever it works. First of all, let's compare something like this is a polynomial. So since x between 1 and infinite, x to the 5 plus x plus 3 is always greater than x to the 5, because this is positive, this is positive, this is bigger, this is smaller. Then we flip over, then this bigger sign makes it smaller. 1 over will be smaller. Then we can multiply by x because x is a positive. X is between 1 and infinite. X is positive. I can multiply this with x. Otherwise, I won't. If I'm not sure x is positive, I cannot do this step, right? Then I have 1x to the 4 here. 1x to the 4 is a p integral, is converge because p is equal to 4 and 4 is bigger than 1. Because of the p integral test or result that we have, that converge. So we know that this converge. So the bigger one, bigger integral, bigger ball converge, contract to the point. Inside ball has to also contract. So we got the right perspective. By comparison test, I converge because this converge. And now this is the part B. We have this function. Now we have a sign here in order to be able to, that looks, so we want to compare things. So what is the boundary? So for the sign is -1 and +1. That's what always we need to remind ourselves. If we use this inequality, because we know that it is bigger than 1, because the integral goes from 1 to x, so x is bigger than 1. This is always true. And this quantity completely, if we replace -1, we will get the lower bound. If we replace +1, we will get the upper bound. So we have boundaries of the function for fx. Now, if you take this one, and if you realize that this form converge, because this is a smaller ball. If you prove that this is converged, you have no information about this function converge or not, because this is smaller. If the small ball converge, if the small ball contracts, you have no information about the bigger contract. So you need to think about this part of the equation, inequality. Because if this converge, if the bigger ball converge, then the small ball has to converge. So that's the idea. So if you take this one, you will find completely wrong and conclusions. You will wrong results that you're going to get. If you use this one, if you find that this is converging, then this will converge. On the other hand, if this diverge, if this blows out, F blows out. Right? This is how you're going to use it. This one blows out, this one blows out. This one converge, this one converge. Okay? Now let's look at the limit form of the comparison test for this function. For this function that I'm focusing on, I want to see whether this contracts or explodes, converge or diverge. So thinking about the 1 over x squared as a p, this is a p integral, 1 over x squared, p is equal to 2 here, and 2 is bigger than 1. So the integral corresponding to this function will be converging. So if you look at this limit, so if this, since this is converge, if we find a limit, then this will has to converge, right? So the limit, just the x squared will be multiplied that. I have the polynomial of degree 3 and polynomial of degree 3. So this is why I choose 1 over x squared to find a result. So there are some choices for this method that you need to, if something doesn't work, try something else. You may try a few things before you get your answer. So the limit is 3 over 2. There exists a limit between 0 and it's finite. So the integral converge. So this converge, then by comparison test, the inequality above implies that our integral converges. Okay. Now part C. This is straightforward in some sense. Since x bigger than 2, x cubed is bigger than the x squared minus 2. And then they take up the third root of third root on both sides. And then we flip over. So this bigger sign becomes a smaller sign. Now you have 1 over x. 1 over x is the p integral. And this p integral diverge because p is equal to 1. And that is diverge because of the p integral. Since this diverge, and the smaller one diverge, it explodes. The smaller ball explodes, the outside ball has to explode. That means that by comparison test, this integral has to diverge. Part D. So this integral, again, we have square root over polynomial. Start with this one. So x bigger than 1, 1 plus x to the 4 is bigger than x to the cube. Take the square root on both sides and then flip over. Smaller will be bigger will be smaller. Now this is a p integral, and this p is 3 over 2 and bigger than 1, right? So the large one is contracting, converging. So the inside ball has to converge. By comparison test, our integral converge. Part E. So we have this inequality, and this is a well-known fact. It's very useful to know this. Now we can use this part, ln x smaller than if x bigger than 2, ln x smaller than x minus 1, also smaller than x. So right. So x minus 1, x always bigger than x minus 1 for x bigger than 2. That's what I want to say. Since I have this inequality and I have this inequality, I have ln x as smaller than x. 1 over, then we flip over, 1 over ln x will be 1 over x. Now p integral for this one is diverge because p is equal to 1. So this one diverge means that the inside one, right? This is the smaller one, this is the bigger one. The smaller ball explodes and the outside ball has to explode. So by compression test, I diverge. That is integral diverges. So for this one, so x bigger than 1, root x always smaller than x. And if I add, since x positive, x bigger than 1, I can add x both sides. And x plus root x is smaller than 2x. And now flip over. Now you have 1 over 2. 1 over 2 is just a constant. You can take it out. And this is a p integral, but p is equal to 1. For p is equal to 1, it diverges. So you have inside the small ball explodes, outside ball has to explode. Then by compression test, I explodes, which diverges. Okay, now question, this is the question 177. This is a card questions, as I would like to remind you, these are the ones that are not typical to ask questions in the exam time or assessment question. These are not usual assessment questions. These are just questions for fun, for learn, for dig in more deeper in understanding. For here, we would like to figure it out what kind of p's and this integral converge. That's the question. So let's call this integral from 2 to the r is I. Y is equal to ln x. Let's change the variable. dy will be dx over x. So y is equal to ln 1. So when x is equal to 2, y is equal to ln 2. I'm looking at the boundaries in it here. When x is equal to r, y is equal to ln r. So 2 to the r boundaries will be ln 2 to the ln r. And this is now becomes dx over x will be dy. And ln x to the y is just a y to the p. And we know how to calculate this integral. So this is 1 over this value plus 1 and this plus 1. So we have 1 minus p, ln r to the 1 minus p, minus ln 2 to the 1 minus p. And the outside, we have a constant 1 over 1 minus p. Now the question is, when this integral, when this limit exists, when r goes to the infinity, what type of p's we have existency for the limit? So that's the next part that we need to figure out. Okay, what are the cases? Well, if 1 minus p is smaller than 0, let's see what will happen. If 1 minus p is smaller than 0, then this will be going to the 0 because you have 1 over something goes up, and then it's like a 1 over n. As n goes to the infinity, 1 over n goes to 0. So this will be goes to the 0. So this integral, improper integral, is the limit r goes to the infinity exist 1. It means it converge. For if 1 minus p bigger than 0, then you have limit the situation, some number goes higher and higher and higher and higher. Then when n goes to the infinity, limit n is goes to the infinity. So this goes to the infinity. So there is no limit for this case. For p is equal to 0, then you have ln r minus ln 2. When ln r goes to the infinity, this goes to the infinity, so ln I will be infinite. So as a consequences of it, what we have here, the integral, the improper integral converge if p is bigger than 1, right? If p is bigger than 1 in this case, we found a limit for all cases. So that's that case. And for p is bigger than 0, so this is p is smaller than 1, and p is, yeah, I need to say 1 there. Sorry, there exists an error here. So p minus 1 is 1 minus p is 0. Right? 1 minus p is smaller than 0, 1 minus p bigger than 0, 1 minus p is equal to 0. That's what I was doing there. But yeah, if this is 0, p is equal to 1 case. Yes, okay. P is equal to 1 is equal to 0. Yeah, sorry. When p is equal to 0, then p 1 minus p is equal to 0. So this is 0 and this is 0. I think I need to change this in the other way around. This will be, so this is 0 and this is 0. This is always 0. So it converge for p bigger than 1. Sorry for the update in the end. But that's the idea. That's how we solve these problems. Thank you very much. It's all in that moment. Thank you.